A line is a set of machines or work centers and workers arranged in sequence. There is a low variety of products on a line. A given line is dedicated to only one or multiple similar products. There is a high level of repetition in the work. The flow is streamlined. There is no or very little crisscrossing. The scheduling on a line is easier than in a job shop or a batch process. And a high level of specialization is needed in the workers. The schematic for a line flow looks something like this. You can see how the flows are streamlined. There's practically no jumbling. And you can imagine that the work is highly repetitive in nature at each of those work centers. Now let's take a simple example to understand how a line flow process works. So here we have the finishing operations for a toy taking place over 5 steps. The 5 steps are: first, the prepare step, in which dirt is cleaned from the toy and its surface is made free from impurities. This takes about 2 minutes per unit. The pre-treat step coats the toy with a protective chemical, takes about 3 minutes. The paint step spray paints the toy inside a given chamber, 5 minutes. The dry step dries the toy in an open area with roof covering, 3 minutes. And inspect and pack happens in the finishing area, which takes 1 minute per unit of the toy. Now, in the line flow process, the units of a given toy move one after another. Each unit enters the line at the prepare step and exits at the inspect and pack step. Now, this goes on and on. As one unit moves from the prepare step to the pre-treat step, the prepare step takes up the next unit of the toy. Similarly, when the unit finishes the pre-treat step and moves on to the paint step, the pre-treat step takes up the next unit, and so on. So at any given point of time, there could be one unit of the toy in each of these steps going through that stage of the process. Now let's look at some terms that are relevant to the line flow process. The first term is the flow unit. The flow unit refers to one unit of the item or the thing undergoing the process. In some cases, it can also be a living being. For example, human beings standing in queues, let's say at the airport, going through multiple steps of the airport's boarding process. Now, in the given example, the flow unit refers to a unit of the toy. Next, we will look at the difference between asynchronous and synchronous flows. Asynchronous flows refers to the situation when work on the successive units at the different steps happens independent of each other. So the steps are not synchronized. In fact, they're not dependent on each other for when to start and stop. If any one step breaks down, the other steps can continue working on the units of the toy if they have units waiting for their process. In the synchronous flow, on the other hand, the work is synchronized across the steps and happens in a rhythmic manner. Each step is given the same amount of time to process a unit. And if a given step breaks down, the entire line stops and waits for that unit to come up. So we will do a small simulation to understand how the asynchronous flow and the synchronous flow differ from each other. Let's assume that we start observing at time t equal to 0, but the line could have been active earlier as well. So look at this. So here we have the 5 steps. You can see the 5 steps and the start and stop times for a given unit. This is unit 1. It starts the prepare step at time t equal to 0. The prepare requires 2 minutes to complete, and therefore it completes the prepare step at time t equal to 2. Immediately after that, it goes to the pre-treat step because there is no unit there at this point of time. It doesn't wait at all. Subsequently, it finishes the pre-treat step at t equal to 5 and moves on to the paint step at that point of time. Again, not waiting between the 2 steps. Completes the paint step at time t equal to 10. Starts the dry process, completes dry at t equal to 13, and then goes to inspect and pack, where it takes 1 minute to complete and therefore completes the entire process at t equal to 14. So you can see that for unit 1, there was no waiting time between the steps because the different steps were free whenever unit 1 reached before them. Now let's look at the wait times. You can see here the wait times are all 0. Okay, coming to unit 2. Unit 2 begins its prepare step as soon as unit 1 has completed, which means at time t equal to 2, and it takes 2 minutes at the prepare step and completes the prepare step at time t equal to 4. Now it's ready for processing at the pre-treat step, but we notice that the pre-treat step is busy with unit 1 until time t equal to 5. Unit 2 has to wait at the pre-treat step until the pre-treat step becomes free at t equal to 5, and therefore it waits for 1 minute. Next, it completes the pre-treat step at t equal to 8 because that takes 3 minutes, and is ready for the paint step. The paint step is busy with unit 1. So the paint step is busy until time t equal to 10, which means that unit 2, even though it's ready at time t equal to 8, has to wait for 2 minutes for the paint step to begin processing there. After finishing the paint step at t equal to 15, the unit 2 moves to the dry step. Now at the dry step, we see that unit 1 has already completed processing, and that happened at t equal to 13, which means at t equal to 15, when unit 2 reaches there, the dry step is free and it starts processing unit 2 immediately. It takes 3 minutes at unit 2 and then moves on to inspect and pack, which again is free because unit 1 has already completed processing there, and it can straight away process at inspect and pack. It takes 1 minute to process there and completes the process at t equal to 19. Now, if you look at how unit 2 moved through this process, you can see that it waited in front of 2 steps, but did not have to wait in front of the next 2 steps. So it waited for a total of 3 minutes in the entire process. Now, looking at the subsequent units, if you look at unit 3, you will see that unit 3 follows a similar principle of moving through the process like unit 2 did, except that the waiting time now has gone up. It waits for 2 minutes in front of the pre-treat step because the pre-treat step is free from the previous unit at a time which is 2 minutes later than when unit 3 reaches it. If you see those time values, unit 3 finishes the prepare step at time t equal to 6, but the pre-treat step is busy with unit 2 until time t equal to 8. Unit 3 therefore has to wait for 2 minutes in front of the pre-treat step, and going forward, it has to wait for 4 minutes in front of the paint step. Again, after the paint step, there is no waiting involved, and unit 3 moves through the other 2 steps and completes its process at t equal to 24. So likewise, we can compute time values for subsequent units like unit 4, 5, 6, 7, and so on. If we look at the values obtained, we will see that all the units move through and the steps are working independent of each other. They are not waiting for synchronizing their start and stop times with each other. As a result, in front of the pre-treat step, the waiting time of the units is continuously increasing. This increasing waiting time is because the units are waiting more and more. The units are actually forming a queue. There's a queue forming up. There's an inventory build-up. There's an inventory build-up in front of the pre-treat step, and that is revealed by the increase of waiting time. Similarly, the increase of waiting time in front of the paint step as well between across the subsequent units shows that there is an inventory build-up happening in front of the paint step as well. Okay, so in front of 2 of the steps, the pre-treat step and the paint step, inventory builds up, whereas in front of the next 2 steps, the dry step and the inspect and pack step, there is no such inventory buildup. This is the asynchronous flow model. Now let's look at synchronous flow. In synchronous flow, let's assume that each step is given 6 minutes, a constant of 6 minutes across the steps to process 1 unit. In such a case, what would happen? Now you can see here, unit 1 goes through the 5 steps, but it begins each subsequent step 6 minutes after it began the previous step. For example, it begins the prepare step at time t equal to 0, the pre-treat step at time t equal to 6, the paint step at time t equal to 12, the dry step at time t equal to 18, and the inspect and pack step at time t equal to 24. There's a 6 minutes gap between starting subsequent steps. And this 6 minutes is followed across the units, across the steps. So you can see, for example, unit 2 begins the prepare step at time t equal to 6, the pre-treat at time t equal to 12, and so on. So now you will understand that every 6 minutes, each step in the process picks up the next unit. And that is the reason why this flow is called a synchronized flow. In the synchronized flow, you will see that at the pre-treat step, at the paint step, at the dry step, and at the inspect and pack step, there is some waiting time involved, but the waiting times are constant across the units. All the units experience the same waiting time at a given step. For example, it is 4 minutes constant for all units at the pre-treat step. It is 3 minutes constant for all units at the paint step, 1 minute at the dry step, and 3 minutes at the inspect and pack step. As a result, all units wait for a total waiting time of 11 minutes as they go through the process. Okay, so in this process, there is no inventory build up in between. No inventory, no queue formation happens in between. The steps just go and wait until their next start time begins. We could have chosen a different amount of time. We need not have said every 6 minutes. We could have said every 5.5 minutes as well. And that would have reduced the amount of waiting time in between the two steps. Okay, so in the synchronous flow model, there is no inventory buildup and there is constant waiting time for all units at a given step. So this is the difference between asynchronous flow and synchronous flow. Now let's examine some of the concepts and understand why the synchronous flow is considered better. First refers to the WIP inventory. WIP stands for work in process or work in progress. It refers to the units present in the process at any given time, either undergoing processing at a resource or waiting for the next resource. The WIP, in summary, includes all the flow units for whom the process has begun but is yet to complete. In asynchronous flow, the WIP builds up continuously. In our example, you can see that it builds up before steps 2 and 3, but there is no such build up in the synchronous flow. In the synchronous flow, for any step, there is no inventory buildup at all. So this is one aspect of the difference between the two types of flow. And the second aspect is in the lead time or the flow time. The lead time is also called the flow time. It's denoted by the symbol phi. And this refers to the time it takes for a given flow unit to move from the start to the end of the process. And it includes all the waiting at each step of the process. You can say mathematically that it can be expressed this way. Lead time of unit I, phi I, is the last step exit time of I minus the first step start time of I. In the asynchronous flow example, we saw that phi 1 was 14 minutes, phi 2 was 17 minutes, phi 3 was 20 minutes, phi 4 is 23 minutes, and so on. The lead time, in other words, of the successive units increased by 3 minutes. Each successive unit took 3 minutes to flow through the process than the previous unit. Now, this happened also because the WIP was building up in front of certain steps because of the difference in the processing times, and the waiting times were different. And this is also reflected in the lead times being different. On the other hand, in the synchronous flow, the phi happens to be exactly the same for all the flow units. And in our example, that is 25 minutes. So the synchronous flow is rhythmic, smooth, and even. In a professional work environment, the synchronous flow is preferred to the asynchronous flow because the asynchronous flow the unevenness and inconsistency in the asynchronous flow is said to be a source of wastage. Next, let's move on to the concept known as cycle time. Cycle time here is denoted by psi, and cycle time refers to the time elapsed between two consecutive units completing a process. You can see here we have the units going through this process. They emerge at the end of the process. So you can think, how long will it take for two consecutive units to come out? Well, that depends on how the process is run, but you can definitely say that the minimum cycle time possible, the minimum time between two consecutive units, xi min, is 5 minutes. It can't be less than 5 minutes. Okay, and this is because the paint step can output a successive unit only after 5 minutes. It can't output two units in less than 5 minutes of time from each other. Now, the actual cycle time, like I just said, depends on how the process is actually run, and it has to be greater than or equal to xi min. Now, related to cycle time is the important concept known as takt time, which is denoted by tau. The takt time is defined as the maximum permissible cycle time if the demand placed on the process has to be met. So the takt time is related to the demand placed on the process. So if the demand has to be met, then how much time can we permit between two consecutive units? So the takt time is defined as the total time available divided by the demand experienced in that much time. So in this example, we have 80 units to be produced every 8-hour shift. So you can say in 480 minutes, we have to produce 80 units. So 480 by 80, that is 6 minutes per unit. So at the most, we can take 6 minutes between successive units. That is the takt time. If we take more than 6 minutes, what would happen? The answer is simple. We will not be able to meet the demand placed on the process. So takt time is considered a very important planning measure. We set the process to a cycle time which is less than or equal to the takt time, and then we can be assured that the demand will be met. Okay, the next concept is flow rate, which is denoted by lambda. The flow rate refers to the average number of units that complete the process per unit time. It is also known as throughput rate. The average flow rate is the inverse of the average cycle time. Lambda is 1 by xi, or you can say lambda into xi equal to 1. If the average cycle time is 6 minutes, then the average flow rate would be 1 by 6 or 0.1666 units per minute, which is the same as 10 units per hour. Next, resource capacity. Resource capacity refers to the maximum number of units that a resource can process per unit time, or the maximum flow rate possible at the resource. So you can see that the resource capacity depends on how much time a step takes to process a given unit. At the prepare step, for example, each unit takes 2 minutes to be processed, which therefore means that in 1 hour, a maximum of 30 units can be processed. So the capacity of the resource known as prepare is 30 units per hour. Likewise, the pre-treat step takes 3 minutes per unit, and therefore its capacity is 60 divided by 3, which is 20 units per hour. The paint step's capacity, by the same logic, is 12 units per hour. The dry step, 20 units per hour, and the inspect and pack step, 60 units per hour. So let's put these numbers here and then move on to process capacity. The process capacity is the maximum number of units that can complete the process per unit time. In other words, it's the capacity of the process as a whole. So this also is the maximum flow rate possible in the process. If you now look at this figure closely, you will realize that the process capacity has to be the minimum of the capacities of the resources in the line flow process. Whichever resource has the lowest capacity, that resource's capacity will be the process capacity. So in the given example, the process capacity is 12 units per hour because that is the lowest capacity of a resource, which happens to be the paint resource. Now, related to capacity is the concept of bottleneck. The bottleneck concept is extremely important in operations management. Now, formally, bottleneck is defined as a resource on which the demand placed exceeds the capacity. So please note that bottleneck refers to a resource. The resource could be a machine, it could be a human being, it could be a mindset. Very often, mindsets are said to be the bottlenecks. It could be a particular system, a way of operating. It could be a particular strategy, a policy. You see, anything which prevents the organization or the process from meeting the demand placed on it. A bottleneck limits the ability of the process to meet its demand. In the given example, the demand placed on each resource is 80 units in 8 hours or 10 units per hour. But we also see that the capacities of all the resources exceed 10 units per hour. Our minimum capacity resource has a capacity of 12 units per hour. And therefore, in the example, there is no bottleneck. Okay, so merely pointing to, some people point to the resource with the lowest capacity and say that is the bottleneck. But no, until you know the demand, you cannot say there is a bottleneck. Only when you know the demand and you find that the demand is greater than the capacity of some particular resource, you can say that that resource is a bottleneck. Otherwise, there is no bottleneck, or you don't know the bottleneck of the process. All right, now let's ask the question, what if the demand on this process was not just 80 units in 8 hours, but 100 units in 8 hours? Okay, so if it is 100 units in 8 hours, then that would mean 100 divided by 8, or 12.5 units per hour. In that case, you would see that the paint resource becomes the bottleneck, right? So there, the demand placed is more than the capacity. Next, what if the demand was 180 units in 8 hours? 180 units in 8 hours corresponds to 180 by 8, which is 22.5 units per hour, which means that not only the paint resource, but also the pre-treat resource and the dry resource, these two resources also become bottlenecks. So that shows that as the demand increases, multiple resources in the process become bottlenecks, and they all prevent the process from meeting its demand. Next, we learn about resource utilization. The resource utilization is the proportion or percentage of time that a resource is busy of the total time scheduled. Okay, how busy is that resource? In the given example, each resource handles 80 units over a period of 8 hours or 480 minutes. So if we ask the question, how much time is each resource busy? Then this table gives us the answers. You can see here the prepare resource processes 80 units in those 8 hours, taking 2 minutes per unit, 2 minutes per unit, and therefore it's busy for 160 minutes out of that 480 minutes. Its utilization is 160 by 480 into 100, which is 33.33. Similarly, the pre-treat resource is busy for 80 into 3, or 240 minutes out of the 480 minutes, which means its utilization is 50%. By the same logic, we can see that the paint resources has a utilization of 83.33 minutes, 33 percentage, the dry resource 50%, and inspect and pack resource 16.67%. So different resources in the process are utilized to different extents. They are not utilized, their utilization is not exactly equal. Closely related to resource utilization is the utilization of the process as a whole, and this is also known as line efficiency or process efficiency. Now, the process efficiency or line efficiency is not merely the average of the utilization values of the resources. No. Instead, it's calculated like this. We look at the total output. The total output is the amount of time that the process as a whole invests on the units it processes. And the total input, which comes in the denominator, is the total amount of time that the resources are being made available, the totals of the times. So you can see that this is defined as the ratio of the totals of the times spent working by the resources and the total of the times available to the resources for doing work over a given time period. So how much time is each resource working? You can see that these times are 160, 180, 400, 180, and 80 minutes respectively. And the times available to the 5 resources, each resource get 480 minutes. And therefore, the process efficiency is 160 plus 180 plus 400 plus 180 plus 80 divided by 5 into 480. And this comes to 41.67%. So in this video, we have become familiar with the following concepts. The first is line flow, then flow unit, then asynchronous versus synchronous flow, WIP inventory, lead time or flow time, cycle time, takt time, flow rate, process capacity and resource capacity, bottleneck, resource utilization, and line efficiency. Now, one might get the question, we saw the line flow and we understood how these terms are relevant in the context of a line flow. But what about a process that is continuous, where the flow unit is not discrete, like the case of a toy or a car or a washing machine, but something that is liquidy in nature, something that is liquid or semi-solid and which flows through the process as one continuous thing and not as discrete units. Are these terms applicable there too? The answer is yes. These terms can be used in that context as well. For example, this is an ice cream manufacturing process, which is a continuous flow process. You can see here milk and other ingredients, they flow into the process at the blending stage, which is stage one, and they go through the 9 stages or steps one after the other. The flow goes through all these steps and comes out as finished ice cream. So here, the flow unit can be taken to be, for example, 1 liter of the ice cream or 1 kilogram of the ice cream as we find convenient. The WIP in that case would become the total quantity in liters, currently between the steps 1 to 9. The lead time or the flow time would be the total time it takes for 1 liter to move from the raw material inventory to the finished goods inventory. The flow rate would be the number of liters of ice cream that are produced every minute. And the cycle time would be the number of minutes for 1 liter of the output to manifest. So you can see that the terms that we learned for the line flow process can be extended to the continuous flow situation as well. With this, we come to an end of this video.